Morning and welcome to Chapter 3. Today we're going to be learning about functions. These are going to be our primary tool for the rest of the semester. They are represented with a letter, but they don't work like variables. So a lot of today's lesson is going to be conceptual rather than algebraic, as we get a feel for what functions are and how they work. We're going to carry those with us for the rest of the semester. So a function, you could think of it as words we use are mapping, or assignment of outputs. A function is, you can think of it like a machine where you give it an input and it responds with an output. So for example, maybe the function's name is f. You give it the input 3 and it gives you back, we call this f of 3. And that's going to be some number that the function gives you back when you give it a 3. So maybe it's a 2, maybe it's a 5. We don't know anything about this specific function, so I'm not going to say yet. But you use this notation to describe the output for an input. If you don't know what the output is, you just write it's whatever f does when we give it 3. So maybe f of 3 equals 10. So then when you give it the input 3, it gives you the output 10. Now, most functions are going to come with an algorithm. An algorithm is a rule to follow to determine the output. So for example, I could say, let's define g of x. Here's how a definition will look of an algorithm. Let's say I define this to mean x squared plus 4. So then what's going to happen? If I give it the input, so if I give g the input 3, it's going to give me 3 squared plus 4, which is 13. So I would write g of 3 equals 3 squared plus 4, which is 13. Or g of 2 equals 2 squared plus 4, which is 8. So this rule, whatever input I give it, this rule tells me how to get the output. So most functions we use in this class are going to be defined by a rule or an algorithm. You can use either word. Algorithm, rule, either one's good. So most functions are going to be defined that way. So maybe I could say, let's define h of x to be, how about the absolute value of x minus 3? So then I could write something like h of 10 equals the absolute value of 10 minus 3 is 7. So I give you an input, you can plug that into the rule and get the output. But we also want to be able to work with functions when we don't know the rule. So if I don't know the rule, I just know I have a function k of x. Well, all I can really say is I could make something like k of 3 or k of 5, but I don't know what those are going to be without a rule. Now again, functions behave very differently from variables. A variable is how we talk about a number without knowing its value. A function is a way to talk about a process. So a variable stores a value, a function stores a process. So it's a fundamentally different kind of object. And typically for variables, I'll use letters like x, y, z, maybe t. For functions, the three letters we use the most are F, G, and H. So I will pretty much never use F or G for a variable. I will almost always use those for a function. And I'm never going to use X, Y, or Z for a function. Those will always be variables. But sometimes for other letters, you have to tell from context. Like I might say, H of t is the height as a function of time, or I might use H as a variable in some other context. But it'll always be clear from context whether I mean a function or a variable. And if you're ever concerned, ask. So when I use this notation, F with parentheses, it has a few different meanings, and these are also dependent on context. But as we get further through this lesson, it'll be clear which one is which and when. So I'm just introducing these now, but they'll make more sense in a bit. We could say it represents a process to get an output from the input inside. Like where g of 3 was equal to 3 squared plus 4, which was 13. G was the process that turned the 3 into a 13. But another use of this notation is to refer to the output. So I can use it as a process like g of 3 equals 13, or specifically, whoops, it was 3 squared plus 4 was 13. Or I could also use it to refer to the output. So I want to talk about the number f of 10, even if I don't know the rule for x. I can treat f of 10 like an unknown quantity. So this whole thing behaves like a variable. I can add numbers to it. I can subtract numbers from it. And I want to be clear, there is no direct access to the inside. And the inside is always representing the input. So we put the input inside, like I put the input 3, and then the output goes after the equal sign. So g of 3 refers to the value of the output I get when I put 3 in, and that output is 13. So the whole thing is the output. The number in the parentheses is the input. We don't have any direct access to the inside or the input because functions are, again, grouping symbols. That means the only way you can get the input back is is to interpret the function. Just like last section, the only way to get inside the absolute value was to interpret it as meaning the magnitude and split the equation into an OR statement. Functions are kind of the same way. Like if I say, thinking of an example here, if I say, let's use that same function g. So again, remember g of x was x squared plus 4. What if I say that g of a equals 20? What is a? Well, I know that g of 4 equals 4 squared plus 4, which is 16 plus 4 is 20. But I also know that g of negative 4 equals negative 4 squared plus 4, which is also 16 plus 4, which is 20. So, oops, a equals plus or minus 4. I don't know which one it is. It could be either one. In fact, I'm going to write this not as plus or minus 4, but to be very clear, it means the same thing, but I want to be even more clear with notation. A equals negative 4 or a equals positive 4, and we don't know which. So it depends entirely on the function, how much information you can get back. Here, I narrowed it down to 2 numbers. We could have a much worse situation. What if we say we define h of x to just be equal to 1? No matter what input I give it, the output is always 1. I can do that with a function. So if I take h of 3, that's equal to 1. And if I take h of 10, that's equal to 1. And I can use h as working, I can do operations with an output. So I can say something like 2 times h of 3 plus 5. That would be 2 times 1 plus 5 is 7. So I'm allowed to do algebra with these outputs. The outputs honestly look a lot like variables in the way they behave. But what I can't do is work out what I had put into h originally. So if I know that the output is 1, since both of these outputs are the same, I have no way to tell if the input was 3 or 10. And I know you're saying like, well, you can just look at the page, but remember, what I mean is not we don't have a way to tell. I mean the algebra has no way to tell. There's no way to look at this output and figure out what's in the input. Because remember, this is a grouping symbol. The inside is isolated from the outside. There's no way for them to communicate. In other words, sorry, let me turn the page here. So h of 3 equals h of 10, but 3 is not equal to 10. So what I mean to show with this example is I cannot cancel out h. That's one way where it doesn't behave like a variable at all. I can't cancel out the h here. This entire object h of 3 acts like a variable, and h of 10 acts like a variable, but h itself is the function notation. So this whole thing is one particle. I can't cancel out the h here because, well, clearly 3 is not equal to 10. Or here's another way that this is different from a variable. H of 3 plus 10, that's h of 13. I said no matter what the input is, the output's going to be 1, so that'll be 1. But on the other hand, h of 3 plus h of 10 is equal to, well, those are each of the outputs is 1. So this is 1 plus 1, which is 2. So these are not equal to each other, is what I'm trying to show. In other words, you can't just distribute the function to the inputs. If the inputs are added together, that doesn't mean I can distribute the function. So I cannot distribute a function. So I'm trying to get through all the ways that functions work differently from variables here. So again, this is not multiplication. It doesn't behave like multiplication. This function notation does not follow any of the same rules as multiplication. So this is not the same as h times 3. I know the notation looks similar, but make sure you understand that this isn't multiplication, because h of 3 plus 10 here is a different number than h of 3 plus h of 10. So I'm allowed to add two numbers together that are both inside, get h of 13. I'm allowed to add 2 outputs together on the outside and get 1 plus 1 is 2. What I can't do is h of 3 plus 2 is equal to 3, but h of 3 plus 2, that's h of 5, and that's equal to 1. So there's no, you can't move things from the inside to the outside without knowing something specific about the function. In this case, what I know specifically about the function is there's no way to move things from the inside to the outside. So these two expressions are not equal to each other. This is a grouping symbol. We can't just pull things inside or outside willy-nilly. So for h, I know the output is 1, but the input could be literally any number. For g, earlier when the output was 20, I knew that the input was either 4 or negative 4. Let's define a new function f. I'm just going to rotate between those three letters. But let's define a new function f. We're going to let f of x be computed by the rule, how about 3x plus 2? So f of 2 equals 3 times 2 plus 2, which is 8. So if I have the input 2, I get the output 8. F is an example of a function where I can actually get the input back. If you told me that f of a was equal to 8, so when I did this for g, I got two different answers that were possible. But for a, I know that f of a is equal to 3a plus 2. Whatever you plug in, you get 3 times that thing plus 2. So f of a is equal to 3a plus 2, and that has to be equal to 8. So this is a common practice with functions, is to substitute the definition in. F of a is 3a plus 2. So I've plugged a in. Well, then I can do algebra with this. I can subtract 2 from each side. 3a equals 6. Divide both sides by 3. A equals 2. So if the output is 8, the only possible input was 2. So f is a function for this particular function, obviously not for h or g, but for this function, if you know the output, we can find out which one input got us that output. So there's only one possible answer. If I said that f of a was 11, the only number that works is the input was 3. So if I know the output, I can solve for a unique input. Oh, yeah, that's the word I should use instead of 1 here. I should say unique. There's only one input that'll do it. I call functions like that, I could say invertible, which means I can turn it inside out or undo it. There's another word, and I'll explain what this means later in the class, but there's another word for functions like this. We also call them one-to-one, which means that if you know which input there is, there's only one input that gets you there. If you have one output, you know which one input it came from. Maybe a better phrase would be one from one, but this is the one that's stuck in the community, so we all call it one-to-one. So we'll learn more about one-to-one functions in section 3.7. That's coming up in Unit 4. So we'll get there. So let's see. Let's start looking at functions as more concrete objects. Let me make up a new function. Let's say, so I'll often use the word suppose or the word let to say, just assume I can define this function. Let's say that this function exists. Let's say k of x is x squared minus 3. It's a nice function. So I can plug in things like k of 1 is 1 squared minus 3, and that's negative 2. K of 0 equals negative 3, because that's 0 squared minus 3. K of negative 1, well, that's negative 1 squared minus 3, and that's that took me longer than it should have, negative 2 again. You see why k of negative 1 is the same as k of 1, right? When I square it, I lose the sign. So k of 2 is 4 minus 3, and that's 1. K of 3 equals 3 squared minus 3, and that's 6. So I could even make a table for inputs and outputs. This is a nice tool, an input-output table. Lets us see the behavior of the function. So let me plot a few points. -3, -2, -1, 0, 1, 2, and 3. Let's say I have all of those inputs and I want to know the outputs. Well, I already computed most of them. Let me fill in the rest of this table here. They go 6, 1, -2, -3, -2, 1, and 6. Here's something I can do with this function. Since I have this table of inputs and outputs, if we let y equal k of x, we get the graph of k on the Cartesian plane. What's the graph of k? The graph of k is the set of all points on the Cartesian plane that satisfy this equation. So let me draw a Cartesian plane here. When x is -3, k of x equals 6. So this is going to be the x value and the y value, and I'm going to plot that on the plane. So here's -3, 1, 2, 3, and then up 6 points, 4, 5, 6. So here's -3, 6, -2, sorry, I just confused myself for a second there. Never mind, this is fine. -2, 1, -1, -2, 0, -3, 1, -2, 2, 1, and 3, 6. Those are the 7 points I have listed on my table. The graph of k is not just these 7 points. I'll go on and update you. There we go. Not just these 7 points, but every point that's possible on the graph. So for example, if I plugged in 2.5, this one's going to be a little uglier, but it's 6.25 minus 3, because that's 2.5 squared. I know that because I have the powers of 5 memorized. It goes 1, 5, 25, 125, 625. So I know that 25 squared is 625. So I know 2.5 squared is 6.25. So that's how I got that without a calculator. What was my point, though? If I plot 2.5, the y coordinate is 3.25. So that's right here. And I could plot 2.25 and find the y value for that, and that would be somewhere around here. And then there's a point here or a point here that works. So it's not just discrete points. There's infinitely many x values I can pick, and there's a y value for each of those. And if we draw all of those in, like I'm doing here, I'm penciling in all of those points, not just the ones I had plotted before, we're going to get a smooth curve. A lot of functions will make a smooth curve when you graph them, and this function is no exception. Okay, I missed that point a little, but let's pretend it was where it was supposed to be. This curve is a parabola, actually. It's that boomerang shape I was talking about last chapter. And that's because the rule for k is x squared minus 3. Since this rule is quadratic, the graph turns out to be a parabola. So the graph is, oh, I'm on eraser mode. It's the set of all points x comma y such that y equals k of x. So that's the definition of a graph, is it's every point in the Cartesian plane that fits this relationship. Now, something interesting about this function is there are y values that come from more than one x value. Like I could plug in -3 and get 6, or I could plug in +3 and get 6. Either one of those, I have the same y value for 2 different x values. But on the other hand, for a given x value, there's only ever one y value. So like this x value here, I only see it touch the graph once. There's only one y value. or this x value here, update, this x value here, I only see it touch the graph once. There's only one y value for that x value. The reason that happens is whatever x value I pick, the y value for it is k of x. And k of x is an output defined by a rule. You can only get one output for each input. So two outputs can share an input. Sorry, no, that's wrong. The inputs 3 and -3 have the same output 6, but the input 3 only has one output. The input 2 only has one output. So 2 points here can have the same y value, but they can never have the same x value. And on a graph, when you look at that, what that means is the same x value, all of the points on this green dotted line have the same x value. So this green dotted line can only touch the graph once. We call that the vertical line test. If a graph is the graph of a function, no vertical line, no vertical line can touch it more than once. So for example, here's one graph, here's another graph. This graph on the left, I found a vertical line that touches it more than once. In fact, it touches it 3 times. Even 2 would be enough to get us in trouble, but this one goes overboard. So this is not a function. But this one over here, no matter where I draw a vertical line, it'll never touch the graph more than once. So this is a function. And the reason we have that rule is based on the definition. Let's say this is the x value -1. So maybe this is -1, 5, and this is -1, 1, and this is -1, -3. Let's say those are the coordinates of those 3 points I penciled in. Then over here, if this were the function like y equals f of x, then the problem is if I write f of -1, this symbol f of -1, represents the output I get when I plug in -1. So this would have to equal 1 and 5 and -3. And this is not allowed. I want this symbol. I want f of -1 to refer to a single number. Even if I don't know the number, for this definition to make sense, it can only be one number. There has to be a specific output for each input. So this is not okay. But this is fine. Here, each input has one specific output. We call graphs that don't satisfy the function definition, we call them relations. You can use a relation to just describe a bunch of points that you want to talk about on the plane. Right. Try to find my page. There's the other page in the notes I wanted to talk about. So earlier we had, no, I don't want to write recall. Again, let's say k of x equals x squared minus 3. So earlier I was plugging in a bunch of points, like k of 2 was equal to 2 squared minus 3, which was 1. k of -2 was -2 squared minus 3, which was 1. I can do other things, like I can say, what is k of a? And then the way the functions rule works is whatever I put in these parentheses, that's the input. You replace the variable of the definition with the input. So the way this definition works is this variable name x matches up. So the function is telling us, whatever you plug in, square that thing and subtract 3. We will usually use x for the name of the input variable. Not always, but usually. So if I say k of a, then I'm going to get a squared minus 3, because I just plug a in where x used to be. That's how we call this evaluating the function, evaluating it at the input a. But we can get goofy with this, right? I can even plug in another variable, like I could plug in h, and that'll give me h squared minus 3. Or I could plug in 2h. And so the function rule says, so what do I do with 2h? The function rule says, take the input, square it, and subtract 3. So I'm going to take this whole input, 2h, square it, and subtract 3. So my answer is going to be 4h minus 3, because that's 2h times 2h is 4h squared. So I need these parentheses. Like I said last chapter, whenever you're substituting something, evaluating a function is like substituting, whatever you're dropping in, you want to put parentheses around it to make sure you catch the whole thing. So this whole input is getting squared, and that's why these parentheses are here. If I wanted to take k of 3a plus 4, the answer would be 3a plus 4 all squared minus 3. So I'd have to FOIL. 3a times 3a is 9a squared. 3a times 4 is 12a. We have 2 of those, so I get 24a. And then 4 times 4 is 16. So I FOILed that. Whoops, this is 24a. So I FOILed that, and then I subtract 3. So k of 3a plus 4 is 9a squared plus 24a plus 13. So if you plug in an expression, you can get a different expression back. One more I want to do for no particular reason, but we'll see these again soon. Again, remember k of x was x squared minus 3. I can even plug in an expression with an x in it. So don't be alarmed here. If I say k of x plus h, that would get me x plus h quantity squared minus 3. And remember, because this is a common mistake I see, this is not the same as k of x plus h. So it's not the same as x squared minus 3 plus h. So don't make that mistake. The actual answer is going to be x squared plus 2xh plus h squared minus 3 when you FOIL the x plus h squared. So these are 2 different expressions with 2 different results. So don't confuse them. All right. As we're working with functions, you might see functions. You might see function notation in the context of algebra. Like I could write something like this: 3 times f of x plus 4 equals 13. Some things I can do are I can, if I'm trying to solve for x, I can subtract the 4 from both sides. I can divide both sides by 3. But now, that's as far as I can go without knowing something specific about x. From here, I need the rule. Spelling. I need the rule for f to go any further. So I'm trying to solve for x, but there's no way to get x out of here without knowing something specific about f. We have to know what f is, what f does. So specifically, you cannot divide both sides by f. That is nonsensical because f here is not multiplication. This whole symbol says the output when you plug x into f is 3. So we cannot divide by f. That's not a thing that happens. Or if I write, maybe I'm working a problem and I end up with this expression, f of x plus f of 2x, all divided by x. There is no way to simplify this. So there are no like terms. I can't make f of 3x up here because x and 2x are in the function separately. So I don't know if that's going to be the same as f of 3x. Probably not. I can't cancel out this x because I can't divide the x out from inside the function. F of x divided by x can't be simplified either. So neither of these can be simplified. So I can't cancel out the x's because this one's inside the function and this one's outside the function. All right, so that's a general overview of functions and what we can't do with them. Now, what we will do with them is, for the rest of the class, most of the functions we look at will have specific rules, and we'll try to understand their behavior, try to understand their graph, try to learn about cool properties they have. So the goal is to use this notation as a tool to study processes in algebra. So we're going to think of functions as processes, and we're going to use this tool to study them. All right, so that's all for right now, but join me in a bit and we'll talk about some specific properties of functions. And that'll be in section 3.2. So we just got 2 more sections before you're ready for the Unit 2 test. All right.